Hello, everyone, and thank you for joining us this evening. I'm going to talk about accumulations and functions defined by integrals, as you can see that here, but my original title for this talk was just my favorite function, which is the function you see there, some thoughts on f of t equals f of a plus the integral from a to t of f prime of x dx. And as I say, that's my favorite equation, and I hope you'll like it too by the time we're done. And if not, and you're AP teachers, you're going to have to like it anyway because it shows up on the exam so often that it's the easy way to do a lot of problems. So I'm going to talk about it a little bit, and then we'll look at some actual AP problems from past years, and then we'll take whatever questions you have. And as Cindy said, if you have a question, anytime, just type it in the little chat box there, and she will see it and possibly interrupt you or just save it till the end, okay? So here are my thoughts on this function. In the current Acorn book, the current course description, the goals of the AP Calculus program include the statement, students should understand the definite integral as the net accumulation of change. The topical outline also includes the topic of the definite integral of a rate of change of a quantity over an interval is interpreted as the net change of the quantity over the interval. And then they give this equation, which looks suspiciously like the fundamental theorem of calculus, okay? And it is the fundamental theorem of calculus, but it's interesting that they don't call it that at this point. They want to emphasize what it really says. And what it says is the integral from a to b of a derivative, which is a rate of change, gives you the net amount of change, the difference in position or whatever it is from the beginning to the end. And that's where everything else comes from that, all right? It says the final value is equal to the starting value plus the accumulated change, the integral giving you the accumulated change. So that's another way of interpreting that. If your situation is a velocity, acceleration, position kind of situation, it tells you the final position is equal to the initial position plus the displacement. And, in that kind of a situation, the velocity is the derivative of the position equation, and therefore the final position is equal to the initial position plus displacement, which is the integral of velocity, the difference between where it started and where it ended. So it's really the same equation in that kind of context too. Probably the first time you saw this, you may not have realized you were doing calculus, or maybe your children didn't. It was a situation like this where you had a constant rate of change, all right? And if you just do this work here, you can factor that m out in front of the integral sign, and then the integral is just the integral of 1 dt, which becomes the integral of t from x to x0, and that ends up, when you put the numbers in there, looking like that, which is strangely like the point-slope equation of a line. So that equation right from the start was building up to my favorite equation here. And it says, that the y-coordinate of any point on the line, since the slope is a constant, it's a line, is some initial point where you start, plus the slope, which is the change in y over the change in x, multiplied by the actual change in x. So that gives you the new y is equal to the original y plus the change in y once you cancel that out. So that goes right back to Algebra 1, is where this really started in slightly disguised form. While we're on that, I'm going to take a little tangent here, I guess, off on a tangent, which is a joke, I guess. I don't like the slope-intercept form of a line. More specifically, I'm trying to get a movement started to eliminate the slope-intercept form of a line as a method of writing the equation of a line. I don't want to get rid of it entirely, but certainly as a method of writing the equation of a line, where you have a point and you have the slope, and you got to put the slope in there and put in for x and y and figure out what b is, and then finally put it all together at the end. Perfectly good, perfectly nice math. Just a waste of time. Just have the kids straight from Algebra 1 substitute into the point slope of the line, and then there's not all that work to do. The answer's done there. And if they need it in this form for some reason, like multiple choice answers or things like that, they should know how to simplify it into this form, but not started. Okay, back to my favorite equation and how it shows up sometimes on the exam. Back in 1997, AB 89, they asked this equation, and it confused a lot of people. I know teachers called me up and asked, how do you do this problem? And it says if f is an antiderivative of this thing, and I don't think anybody's going to find the antiderivative of that without a half an hour's work, and such that f at 1 is 0, then f at 4 is equal to, and they had 5 multiple choice answers. But again, if you just think of it using my favorite formula, the problem is done this way. F at 4 is equal to f at 1 plus whatever the function changed between 1 and 4, which is the integral of that expression there. So the final answer is f at 4 is equal to f at 1. F at 1 happened to be 0. I would have liked a different number there, but f at 1 is 0. And then you do this integration on your calculator, and you come up with the final answer, even though you can't do the integration there by hand. All right, I was way back in 89. Oh, there's the other way of looking at it, that f of 4 minus f of 1 is the integral there. That's the fundamental theorem idea. And, of course, f of 1 is 0, so you, again, do this by calculator. Here's another example. From 2008, AB7, multiple choice question. Again, I didn't put the answers up here. But it says a particle moves along the x-axis with a velocity given by v at t is equal to 3t squared plus 6t for time t greater than 0. If the particle is at position x equals 2 at times t equals 0, what's the position of the particle at time t equals 1? Now, you can do this kind of as a differential equation question, but it's simply set up to use my favorite formula. So that's what I'm going to use here. The position at 1 that they're asking you for is equal to the initial position at 2, and then you integrate from the time that goes with 2 from 0 up to 1 of the velocity. And this was a problem to be done by hand, so you have to do the antiderivative here by hand, and then substitute in the numbers, and you come up with 2 plus 4 is 6. There it is. This is going to get very boring now because all I'm going to do is use this equation again and again and again. So let's take a look at another question from the same year. And this question surprised me. It's number 87, and it says an object traveling in a straight line has a position of x at t at time t equals 0. If the initial position at 0 is 2, and the velocity of the object is given by the cube root of 1 plus t squared, what's the position of the object at t equals 3? What surprised me about this question is it's the same question as the last one that we just looked at. The only difference is the velocity is a little different. The initial position was equal to the same. So here we go again. Here it is. The final position, x at 3, is equal to the initial position 2 plus the integral from the initial point time 0 to 3 of this expression. This was intended to be done on a calculator, of course. So you have 2 plus what you get on the calculator, and there's your answer. Okay? And finally, I think they used the exam, this equation like 7 or 8 times on the 2008 exam here, and also on the pre-response, which we'll look at in a minute. But here was another question from that exam. It says if g of x is an antiderivative of f of x, and g at 2 is negative 7, then g at 4 is. And these are the actual answers they put here. Of course, there's no function you can actually come up with a number, so they just want to know which expression is it. So I'll give you a minute to look at the expressions, but if you know my favorite function, the answer is pretty obvious. If you guessed choice E, you got it. Okay? There's the initial position, negative 7, plus the integral from 2 to 4 of the function. And there you are. All right? Okay, now I'm going to go look at some multiple choice, some pre-response questions here. I have them listed on the next 2 slides if you want to look them up later when you see the slides here. But I'm going to now have to switch over and just give me 1 second here and play with my computer a little bit. There we are. And take a look at my computer. Is such fun. Hang on.
Yeah, we're still seeing the presentation.
Okay. I'm adjusting my screen. All right, here we go.
Okay, it's up.
Okay, it's up now, is it? All right. And the first one I want to look at is way back in 2000. All the little boxes with your picture that said you went up in the middle of my screen. But anyway, back here in 2000, another one of my favorite questions, they asked this question, which I'll look at in a little bit of detail here maybe. It says, Water is being pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at a rate of radical T plus 1 gallons per minute for 0 to 120 minutes for T. At time T, the tank contains 30 gallons of water. All right, and then they asked the question, says, how many gallons of water leak out of the tank from T equals 0 to T equals 30? All right. One of the things you can tell your kids in this kind of a problem, which we've seen lots of these as the years go by, where something's going in, something's coming out at different rates here, is when they ask for an amount, which is what they did here, the amount of how many gallons, the amount of water, that's an amount, how many gallons. What you want to do is you want to integrate a rate. So there's your first clue there. You want to integrate a rate, which is exactly what we've been talking about here. They did not ask about the initial bit, so they just want to know how much it changes. So you integrate the rate, and of course this was not a calculator question, so you had to do all that by hand, and you come up with a number. Simple as that. But that's the main idea there. Now the other kind of interesting thing this year is they gave two methods of solution. And I think they were pushing the first one here, but they wanted to show the older way beforehand, which was to treat this as a differential equation. So they started here by identifying the derivative, and of course the T plus 1 is a rate, it's a derivative. And then they, found separated the variables, they're already separated really, integrated, found the constant integration, put in the initial condition, found the constant, rewrote the thing, and then finally substituted in 3 and came up with the same answer. There it is, same answer. Either way is correct, either way is legitimate, both ways get full credit, but I hope you agree that method 1 is a lot quicker than method 2. So anytime you need an amount, you integrate a rate. Okay? And then they did more with this thing. They asked in the second part, how many gallons of water are in the tank at times T equals 3 minutes in part B? And that's a very simple one, but they're really setting them up for the next part. So for how many gallons are in there, it's the 30 gallons you started with, and then it's 8 gallons per minute for 3 minutes coming in, add that on, and then the number we found before, 14/3 gallons going out. And so together, there's the whole idea. The initial amount plus the rate in and the rate out gives you the total amount there. So then they wanted you to do that big time after that, and they asked up here in part C, which is going to go off the screen in a minute, but they asked in part C at the top, write an expression for the total number of gallons of water in the tank at any time. And again, they gave two methods for here. The first method is just sort of building on the line before it, was the 30 gallons that you started with. There's your initial condition, and then the integral from that time to T, any variable T, of 8 minus radical T plus 1. The 8 minus 8 is the amount in. The radical 8 x plus 1 is the amount out, and you subtract them, of course, to find the actual amount. So that you can give that answer. They listed a second answer here. Either one of these are correct. You certainly don't need both. The second answer is a little more in line with part B here, where they did the 8T separately, which of course is what you would get if you integrated it. So you can get, you can get either answer for that part. Okay. Then, whoops, sorry. Let's slide the page up here. Then they also went back and worked that by the second method here, doing it as a differential equation, which is worth doing, but of course it's much simpler in the first way here. As a differential equation, they said the rate is the amount, the rate in minus the rate out is the actual change in the volume that's there. And then they, integrated that, found the antiderivative there, put on the plus C, went all the trouble figuring out what C was, comes out to be 92/3, and then they wrote the final deal here without an integral. All right. Of course, if you do the integration, this is what you'll get. But there's the other approach to it. Okay. Okay. And just to finish this problem up again, to show you how things relate relate together, which is, I think, always a good thing to show your kids there, is in the final part of the question, they asked at what time t is the amount of water in the tank a maximum. So it's a max min kind of problem here, an optimization problem at the end of this one. And of course, to do that, you need the derivative of A. So, that means you got to go back to A up here and differentiate it by the fundamental theorem of calculus. And whichever form you use, the derivative is going to have to be 8 minus radical t plus 1. Or if you did method 2, of course, you already have that expression there. And, then you're all set. You solve that simple equation. T comes out to be 63. And then you go ahead and justify that that's a maximum. So that basic idea of my favorite equation is in a lot of all of that question. Now, let's take a look at a few more. And the next one I want to look at is 2008. All right. And the first part here, I just want to kind of do this a little quicker and then show you how many times it actually shows up in this exam. So let's take a look here. This is 2008 AB2, and in AB2, down in Part D, they said the basic problem here was they gave a table with the number of people that were buying tickets at a concert over a certain period, and they ask you the kind of table problems they ask all the way through. But when they get down to Part D, they modeled this. Where did that line? I put it in if I can. Oops, what did I do? Let's jump around on the screen sometime. Oh, they said the rate at which the tickets were sold is modeled by an equation here in tickets per hour. And then they asked how many tickets were sold by T equals 3. Well, that's the same idea. They asked for an amount, the amount of tickets. So you integrate the rate at which the tickets are being sold. And you do that on your calculator and get your answer. Okay, that was number 2. In question 3, they gave this problem. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at the constant rate of 200 centimeters per minute. The slick takes the form of a right circular cylinder with both its radius and height changing. And then the first 2 parts of the problem are really related rate problems that they put in here. Okay? And then they came to Part C, and where it says, by the time the recovery device begins removing oil, 60,000 cubic centimeters of oil had already been leaked. And then it said, right, but do not evaluate an expression involving an interval because the volume of the oil at the time found in Part B. So again, they are asking you for an amount. You should be looking around for a rate to integrate. So let's go down and see what happens there. Well, there it is. That looks like my favorite equation again right there. The 60,000 that we started with, plus the rate, which was the 2,000 that's being spilled out, plus the R at T, which was the rate at which it's being recovered, and you know that's the interval they want there. But that's my favorite equation again. It's all the way through this test. What can I say? And one more time, in question 4. I think it's 4. Yeah. They gave a typical particle motion problem where the velocity is given as a graph. So it says the particle moves along the x-axis, so its velocity at any time t from 0 to 6 is given by a differentiable function v whose graph is shown above. The velocity at the various times is 0. They're just describing a graph here. It has horizontal tangents at certain places. And it says the area of the regions bounded by the t-axis and the graph of v on the various intervals are 8 for that one, 3 for this one, and over here to 6, this one is 2. Okay? And then they asked in Part A, from 0 to 6, find both the time and the position of the particle when it's furthest to the left. Now, there's a couple ways of doing the problem here. You were given the graph of the velocity, and of course the velocity is the derivative. So if you're looking for minimums, the minimum has to occur here where the rate changes from negative to positive, where the velocity changes from negative to positive. That's got to be a minimum, which in velocity terms, when you're moving on the number line, the minimum is furthest to the left. That's really what they ask for, farthest to the left. So it's either going to be there or it's going to be at one of the endpoints, and by the extreme value theorem there. And the first endpoint starts somewhere and it decreases, so that's not the minimum there. But we also have to consider what's happening over here at 6. It may be that that's the minimum. So what they wanted to do is to look at where the velocity change is signed here. And to get your points here, you had to come up with the fact that the candidates are 3 and 6 by looking at the graph and figuring out what's going on there. And then you have to actually find the values at those 2 points to find out which one is really the absolute minimum, and somehow work that out. You have to consider them both. But in working it out, well, here's my favorite equation again. Sorry if I'm boring you with my favorite equation. But here it is. It starts at -2, and that's from the given, and then you integrate the velocity from 0 to 3, and you do that by looking at the region between 0 and 3 on the graph. That's where the 8 came from. So you starting point minus the 8, you're at -10. And then you must do the same thing for 6, and there's my favorite equation again. So here we go. We start at -2, only now we integrate from 0 to 6. So we have to take into account all 3 of the regions in the graph. I'll try to get it all on the screen there. So it's -2 for starting, then we lose 8, we gain 3, we lose 2 more, we're at -9. So the absolute furthest to the left, the minimum position, is at -10, and it occurs when x equals 3. So there's using it in a velocity situation. And yet again, on this test, I think there were maybe 8 times on this test where you used that one. All right. And again, just to show you some more variety, what they can do with this is the 2010 exam. And again, it showed up here quite a few times. This is the snowfall problem. If you remember, it said there's no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow falls and accumulates. That might be a hint, that we're talking accumulation here. Pen working again. It accumulates by a function that's really strange. Cubic feet per hour. All right. And again, the cubic feet per hour tells you that is a derivative of something, or the word rate tells you that that's a derivative, even though it's not marked with an F prime. T is measured in hours since midnight, and Janet begins moving snow at 6 a.m., and the rate at which she moves snow in cubic feet per hour is given by the piecewise constant functions. So we'll have to worry about that. And then they started asking the questions here. How many cubic feet have accumulated in the driveway? Well, how many feet? That's an amount. You look around for a rate to integrate. So sure enough, it's the rate that's up there, and we integrate from 0 to 6. There's no snow at the beginning, so the initial amount is 0 there. And we do that integration on the calculator and come up with the amount of snow that falls between 0 and 6. In Part B, they asked about the rate of change, and then they came down to Part C and said, let H represent the total amount of snow in cubic feet in the driveway that Janet has removed from the driveway at time T hours after midnight, and express this as a piecewise defined function from 0 to 9. All right? This is where there are a lot of points, and there's 2 ways to do the problem. It's an easy enough problem, I think, to do just by figuring out what's going on. They want to know what happens from 0 to 9 in a piecewise function. So I don't think I can get both of these all these numbers on the screen so you can read it. It's a little small there, but we can see there. The second method down here at the bottom, which really is the summary of the other one, this you can do without doing the integration that's up there. Obviously, from 0 to 6 hours, she does not remove any snow. From 6 to 7 hours, then it's 125 cubic feet per hour. for t minus 6 hours. Of course, the mistake the kids made on that question was it made it 125t. They didn't do the minus 6. And of course, since they told you to start time at 0, you have to start time at 0. And same kind of mistake in the next part. And so that's for 1 hour from 6 to 7. And she slowed down a little bit from 7 to 9. We have the 125 feet that she started with, and then there's the rate times the time again for your linear function. But since I guess they're trying to emphasize this business, if we go up and look up here, well, here we see my favorite equation 3 times. You know, from 0 to 6, we have h at 0 plus the integral from 0 to t. And everything is 0 there, so it comes out to be 0. And then from 6 to 7, we have the amount at 6 that she's removed, which is nothing. And then we have a different rate from 6 to 7, from t goes to 6 to 7. So there again is my favorite equation, the accumulation equation. And then when you actually work that out, you get to t minus 6 times 125, and you don't lose the 6 like the kids did. Then, from 7 to 9, we have, here it is again, same thing again. We have the amount at 7, which we get from the last problem, which was 125, and then we integrate the new rate from 7 to t, and then there's your final expression. So you can do that one either way. Probably the second way you could teach in an Algebra 2 class. It's not really that hard to figure out. Okay? And then they finally ask in the last part, how many feet of snow are in the driveway at 9 o'clock? And so you have to then, again, sort of almost the same idea. You have the amount that came down minus the amount that she shoveled. So it's like the same thing, just because the one is minus, they kind of put it on the end there, and you figure it out. Okay? So I think you see what's happening on these. I'll just kind of point out real quickly. Again, it showed up a couple more times. Here we have the table problem. Oh no, this is the naming, the table problem where they're naming the baby elephant there. And again, in part C, they give you a model for that data there, and they ask you how many entries have been processed. Well, again, they ask you for an amount, you integrate a rate. There's my favorite equation again. How many remain? 23 to start, 2300 to start, and then the integral tells you how much they counted, and do the work, and you get your answer there. So it showed up there. It showed up in the next part. I'm just going to point to these now because I think you've got the idea. But it showed up in the next part in where you had people standing in line at an amusement park based on the rate there. They ask for the amount of people, so you integrate the rate. And down here in part D, they did the same thing. They wanted to know when the amount was the maximum, so you put the number equal to 0. You put the number rate at which it's changing there equal to 0, and figure out the amount. So it's there again and again and again. A footnote, incidentally, here, I'll mention this on the way by. People are always wondering if kids have to put the DS on their integral. And the truth of the matter is, you don't have to tell the kids this, but just between us teachers, if they don't put the DS on there, usually it doesn't make any difference. They don't lose points for it. However, in this case, they did. Again, because of the problem. Just picture this without the DS here. Where does the integration stop? Do I have to integrate the 800t or not? And at that point, it makes a difference where the DS goes. So, in this case, if they didn't have it, then they may have lost credit here, depending on how they wrote the rest of this. And of course, if you throw the 700 on the end, and again, is that, without the DS, is that part of the integral or not? So in some cases, it's important to be sure they have that in the right place. If they left it off of this one, they would lose the integral credit because we don't know where it goes. I take that back. The rule that they used was to put it after the first term after the integral sign. which would be here in the proper place. But if they had written something like this for some reason, then we would have had to put it here, and that's wrong. So that's just a footnote on that one particular question. All right? So you get the idea that this comes up a lot of times. Okay? Let's go back to the PowerPoint here. You can go back and take a little more look at those problems when you look through these here. It'll be on the slides on my website there, like that. Okay. I'd like to kind of end before the questions anyway with another problem which showed up in 2009, and my favorite equation showed up on actual some answers. Some of the kids actually did the problem this way. I'm going to do it the easy way first. And while it's not the best way, I sort of thought it was a very elegant way, so I thought I would share that with you here too. In this problem, you were given a piecewise function for the derivative of f. So f prime was equal to g at x from -4 to 0, and it was equal to 5e to the negative x over 3 minus 3 from 0 to 4. And they gave you the graph, and they told you that the function over here, g of x, was a semicircle. So you can see there it's a semicircle, and it's one of those where they're going to ask you some questions about that. And the question was to find the maximum value of this function from the information that's given here. We hope that when they ask you this kind of question with a graph of the derivative, and they see that the derivative goes from positive to negative, they realize that that's the only place this function can have a maximum is right there. And of course, that's the easy way out of it. Okay. They also gave an initial condition here, and I think they asked you to find the maximum value. So, probably the one way to do it. Again, here is my favorite equation again. They wanted you to find first f at 4, so just f at 4 is all the way over here. And so f at 4 is f at 0, which they gave you to be 5, plus the integral from 0 to 4 of the function that works on that part, which was this function. And so here's my favorite equation. There's the 5, and then we do the integration by hand here, and it works out, and we just leave the answer like that. That's f at 4. And then they also ask you to find f at -4. Now we can proceed in the same way. F at -4 is f at 0 plus the integral from 0 to -4. That's my favorite equation again of g of x. And then of course, since the limits of integration here are a little suspicious, most people would take that and turn it around and make it the opposite of the integral from -4 to 0 of g of x. And then you need to find this integral by finding the area between the curve and the axis here, which you do by taking like putting a square around, a rectangle around it, whose area is 8, and then subtract off the area of the semicircle, which is 2 pi. And so you get 5 minus 8 minus 2 pi, which simplifies to 2 pi minus 3. And another approach of doing this problem, and problems like it, which I kind of like, is if you want to find any values at all, to always make the left-hand end the starting point. So this time I'm going to say that f at 0 is f of -4 plus the integral from -4 to 0. And of course, when you do that, the limits of integration are in the correct order here. It's not a big thing. You can do it that way. So f at 0 is 5. F at -4 we don't know. We figure this integral out the same way, 8 minus 2 pi, and then we solve for f at 4 and get the same thing we did before. Sometimes I found always starting at the left-hand end, even if you don't know the left-hand end, and working up to the point that you know, takes care of all those problems of integrating from right to left instead of left to right, and also if there's some region below the axis that you have to take care of, whether it's positive or negative, you always go from the left. Things work out. Okay? Now, here's the part that I thought was clever, but probably overkill. Find the x-coordinate of the absolute maximum value and justify your answer. Okay? So again, here's the same graph. This M number is, I'm going to use M as the number. They told you the number there was 3 log 5/3, but they already told you that. And, of course, the easy way to do that is say that the function changes from the derivative changes from positive to negative at M, and that's the only candidate for a maximum, so therefore that's the maximum value. Some kids did it the long way, but I liked it. Because it's my favorite equation. Some kids actually said this, more than one. F at M is equal to F at -4 plus the integral from -4 to M of F prime of this graph. And since between -4 and M, the derivative is greater than or equal to 0, it means that this integral will be a positive number, and therefore F at M will be greater than F at -4, because it's equal to -4 plus a positive number, which they didn't bother to figure out. You don't need to figure it out, because we figured it out in the last part. Then they said F at +4 is equal to F of M plus this integral. And then they pointed out that this integral is negative from M to 4. There's certainly negative in there. And therefore, it also follows that since we have F of M plus a negative number, that F of M is going to be bigger than F of +4. So they've shown, really they're doing the candidates test here, the only critical number, it's bigger than the values at both ends, and therefore it must be the absolute maximum by the candidates test. So I kind of like that idea. It's way too much work for the problem, but still it's kind of a neat idea, I thought. Okay?
Lynn, there's actually a question.
Okay.
Just if you can make suggestions for teachers whose textbooks are scarce on problems of integration. She says, I'm looking for problems that are based on tables, not necessarily equations. My Larson book is very lean here. Do you have suggestions other than simply creating them myself?
Yeah, my suggestion is to use questions from past exams. Remember, there's plenty of past exams at AP Central, and there's pretty much always a table problem on them. You also have the Form B exams, so you really have 2 exams from each year, at least for the past 10 or 12 years. In future years, you're only going to get 1 exam. That's the bad news. The good news is you're going to get the multiple choice questions, and there may be some table questions in the multiple choice. You can do that, or you can, the various review books that are out there might also have, they certainly do have table questions in them also. Okay, I hope that answers the question. Is there any other questions?
Not so far.
Not so far. Well, okay. Here are my addresses here. My email address is there. Feel free to write me anytime. Everybody else does. I have started a blog last August called teachingcalculus.wordpress.com, in which I'm posting things about 3 times a week and to hints on things about teaching and so forth, teaching calculus. Right now I'm just starting integration with some table problems, actually. And so I always like to start them with a couple of table problems. So in the last couple of posts have been table problems there, and then we'll get into fundamental theorem and so forth, I guess, next week. And I have the website. The website there at the bottom, www.linmicmullin.net. If you click on the navigation bar at the top for AP Calculus, you will see the handout for this. In about 15 minutes, I will post it right after this, right after I'm off of here. The one that's there is simply an older version of the same thing, so I thought I'd give you the newer version there. And I think Cindy said that when the recording is available, I will also put that link there too, so you can find the link to the recording of the whole session.
Exactly.
Okay?
Yep.
All right. So do we have any questions here? Or?
Any other questions? You can either type it in the chat, or if you want to raise your hand and we can see your hand up, we can unmute you so you can ask your question of Lynn. Either about...
If you have a video camera, you can even put your face online, or not.
If you have a webcam.
If you have a webcam.
We're getting some...
Oh, okay. Okay, I don't see any hands on mine, but you can.
Here's a question. What did Lynn say about the new multiple choice questions being available? That's the change in the exam?
Yes, that's a change that the College Board made this year. They have announced that they will release multiple choice questions, a full set of multiple choice questions every year. In the past, they've been doing it every 5 years, but now they're putting it online every year. You get it. You have to go into AP Central to your audit website. You have to sign in with your audit password, and on that website, somewhere there, they have the exam for you to download. Now, I'll just say one other thing there. They'll tell you this when you download it. They want you to use it in your classroom, period, literally. Don't give it to your kids to take home. Don't copy it. Don't put it online. Don't put the answers online. They want to keep it secure so that you and everybody else can use it next spring for a mock exam or a simulated exam. So, next spring you can give it to your kids as a practice exam from real questions. But they don't want to let it out, before then. And then they're going to apparently do that every year, and I don't know whether they're going to let you use the 2012, make it public once the 2013 is there, or just, which way that's going to happen. But the exam is there. Go to AP Central, go to your audit website there, wherever you did your audit, and it's somewhere there on the page. Excuse me. Any other questions?
Yes, another question came in about the last problem that you went through, that you looked at from the exam. Why are you disregarding the endpoints and only considering the critical point at M? Why don't you have to specify the endpoints as candidates as well?
Well, in this, whoops, wait a second here. Let me follow it. When I did it the long way, I did consider the endpoints. The students did consider the endpoints. They first of all showed that f of m is larger than f of negative 4. F of negative 4 is an endpoint. And then they showed that f of m is larger than f of positive 4. That's the other endpoint. And since there's only one critical point, and they compared the value there without actually finding it with the values at both endpoints, then they know that is the absolute maximum. That's why I thought it was kind of clever, because they didn't actually need the values. Now, of course, in the previous part of the problem, they'd already found the values, so that if you were doing it, there's the value at negative 4, and before that you found it at where did it go here? Positive 4. So that you had all that. They had all that information there. That's where I saying I think it was much more difficult way of doing the problem. But I still liked it as a clever mathematics. The way they wanted to do it, you figured both endpoints. You just have to calculate the value here at m and show that that's the largest one, is what they really were going for when they asked that question. Okay?
Yep.
Now I see things in my chat window here.
Then do you see the one about teaching accumulation problems during the review, but how... Is there any way to stress the accumulation idea during the FTC unit?
All I can say is look for things in your textbook that are like it, which you won't find very many, or just pick some of these and use them at that time and save some others for the review at the end of the year. You are correct that the textbooks don't make a big deal of this. The new edition of Rogawski, if I remember right, has a short bit on it. They mention it, and I don't know if they have very many problems or not. But all I can say is go back and look at old tests, and like I did here. You can find them in the multiple choice for 03 and 08. I picked up all the old 08 ones here for you, and on practically every. Certainly every free response here, all the way through, they're there. There's plenty of them. You just have to look around because they are parts of problems. They're not the whole problem. They're just a part, one or two parts sometimes. So that's where you're going to find them. And you're correct. They're not in the textbooks. They're very heavily done on the AP exam. So you've got a supplement there.
Would you be able to identify where in Rogawski these kinds of problems are presented?
Yes, except they don't have.
Not right now, but maybe you and I could do that offline, and then I could share it with the participants.
Yeah, yes, I can do that. Or if you have your book there, you can just look in the index. It probably says accumulation there. So there you are.
Hey, another question that came in, Lin, is someone's asking where do you find the international tests on the AP site, the Form B?
You don't. Well, wait a minute. I take that back. For 1998 through 2011, the B, wherever they started the B exams in there, 2000, I think, they are right there on the same page as the regular exam, as the operational exam. If you look on the page, there'll be the regular exam in the little box with all the things you can download from it. And right underneath it should be the Form B exam. Right at AP Central. I can't go there now. Can I, Cindy? Or
you should be able to get to an outside line, and.
We'll I don't know. Well, we'll see.
Is the question whether it's okay to do that on this?
Yeah. He should. You can get to.
Can you see my desktop?
Yep, it says teaching calculus.
Yeah, that's not where I wanted to go though. Hang on a minute. Where I wanted to go was here, AP Central. If you go to AP Central, and why won't this thing get big? There.
There you go.
Go to AP Central. There you are. And you go over here on the left where it says AP courses and exams. You go down here to the last one, exam information. Click on that. Click on AB or BC, whichever one you're interested in. And here are the exams. And you can see here's 2011 free response, and then here's the Form B, the international form, in 2010 and 2010 Form B. So their questions and guidelines and everything is right there. But after this year, you have to go to your audit website to get the multiple choice. The free response is still here in the same place. And again, I don't know. I think they are not going to continue releasing the Form B exam. All right, I think that they're going to now keep that secure. There's actually I don't know 4 or 5 different exams that they give all around different places, and they're it's expensive to make them up, so they keep them secure. They also need to keep them secure so they can compare some of the questions to judge the relative difficulty of the tests when they go setting the standards, the cut points. Okay. Anything else?
Any other questions? I'm on my audit page. I see the PDF file, but when I click on it, the file says no preview available.
Can you just download it? Is there any place to download it? Oh, you don't have an audit, do you, Cindy?
I don't have an audit, no.
Oh, no, you have to go on your own private audit webpage.
No,
sign in with your audit.
She's saying she's on her audit page.
Okay, I don't know where it is in that page, but they tell me that's where it is.
Up here we have a question about the chain rule.
Yeah.
The accumulator, the integral, when the upper limit of integration is something other than x, is the chain rule is necessary, right? It's correct because you think.
Yes. If the upper limit is not a single x, then when you differentiate, you have to use the chain rule. I really didn't do any differentiation here, and I don't recall ever seeing an accumulation problem where the upper limit was anything other than just the single variable x. I'm trying to think if I could think of an example like that real quick. I don't think I want to do that off the top of my head. But if you're differentiating, you'd have something else in there. But the accumulation idea, you always just go from here to here, and the upper limit's just a single variable.